Lecture 27C is about a topic that in the general n by n case is pretty tough, something called Jordan canonical form. Don't say Jordan, say Jordan. However, in the 2 by 2 case with examples, it's not too bad, and it's definitely worthwhile to look at to round out our understanding of applying linear algebra to differential equations. For my students in our book by Blanchard, Devaney, and Hall, it corresponds to the content about repeated eigenvalues that you'll find in section 3.5, but it's not the exact same approach. It is a different approach. It's good to compare the two. We're going to look at an example based on a new concept called generalized eigenvectors. All right, so get ready here. Again, it's not too bad in the special case here, but it is important. It's worthwhile to do. By the way, my pen stopped working. I have no idea why. It was working just 5 minutes ago. In the case of a 2 by 2 matrix A with a single real repeated eigenvalue, call it lambda, it turns out you can prove that A is either already a diagonal matrix, in fact, a multiple of the identity matrix, I'm emphasizing that that's diagonal already by calling it D, or A is not diagonalizable at all, but it is similar to an upper triangular matrix, the next best thing to a diagonal matrix. Call the matrix J in honor of Jordan. We get the so-called Jordan canonical form. It looks like this. There would be some matrix P, because A is going to be similar to J, such that P inverse times A times P equals J, where J is defined to be this. An upper triangular matrix, the number below the main diagonal is 0. The eigenvalues are on the main diagonal, they have to be. The number in the upper right corner is taken to be 1. Is there something special about 1? Not really. We could say A is similar to any such matrix where this is a non-zero number. However, 1 is kind of the simplest non-zero number, so by convention, we let that to be a 1. This is going to be true for some matrix P. By the way, any matrix like this is only similar to itself, because if you do a similarity transform and take P inverse times A times P for such a matrix, it commutes with P and P inverse, and so the P and P inverse combine to get the identity matrix, and you get back the matrix you started with. Let's consider these cases by step by step. Let's first consider the diagonal case, where A is that matrix. We know how to do that already. We've even done it when there are two distinct eigenvalues in the main diagonal. The matrix exponential of the diagonal matrix will be the corresponding matrix, where the diagonal entries are e to the lambda t when those numbers are lambda. It's also diagonal. Very easy to solve. We could also think of it in terms of just a completely decoupled system. Now, what about the other case? What about the upper triangular case? We've actually talked about that before. We'll do it again. You can solve it because it's partially decoupled. If this is your coefficient matrix, lambda 1, 0, lambda for a given system of differential equations, and if you call the variable for that system, this variable is u and v, it would correspond to du dt. Look at the first row is lambda times u plus 1 times v, lambda u plus v. And the second equation, dv dt, look at the second row of the matrix, 0u plus lambda v. You just get lambda v. You can solve the second equation for v as a function of t very easily. It doesn't involve u. Plug that into the first equation and solve for u. We're going to do that. Yes, for J itself, the system is partially decoupled. We can still do it. We'll then use the similarity, this equation, the fact that this equals J, to ultimately find the matrix exponential for A. We'll solve this equation for A by left multiplication of P and right multiplication of P inverse. But what is the matrix exponential of J? J is not diagonal. It's upper triangular. We can again use the method of undetermined coefficients, as we did before. There's our upper triangular system, our partially decoupled system, based on an upper triangular matrix, with that being J. Again, like I said a minute ago, solve for v first as a function of time. dv dt is lambda times v. Therefore, v is the initial value of v sub 0 times e to the lambda t. Now plug that back into the du dt equation in place of v. There's v right there. It gets replaced by v0 e to the lambda t. That's now a first order, non-homogeneous equation, linear equation. I could either use method of undetermined coefficients or I could use integrating factors. But let's use the method of undetermined coefficients. Find UH, the general solution of the corresponding homogeneous equation, where I get rid of the v0 e to the lambda t. I'm just looking at du equals lambda times u. du dt equals lambda times 2. I know the general solution is going to be an arbitrary constant times e to the lambda t. Now, also come up with a particular solution of this non-homogeneous equation. It's trickier because that's a lambda and because that's a lambda. Just guessing a e to the lambda t turns out to not work. You can try it. You can then try a second guess, add an extra factor of t, and fortunately that does work. If you plug it in, if you subtract lambda u from both sides of this equation and plug it into the left-hand side, find u prime, up prime, and minus lambda up. These two things completely simplify. I had to use, by the way, the product rule there. They cancel. You're left with a e to the lambda t. That's got to equal v0 e to the lambda t for all t. Therefore, a must equal v0. Hey, that worked out pretty nice. Therefore, the general solution of the non-homogeneous equation is UH plus UP, as we've done before, C to the lambda t plus V0 t e to the lambda t. The only thing left to do is just figure out what C is when you assume U of 0 equals U sub 0. Plug in U equals U sub 0. On the left side, plug in t equals 0 here and here. This term goes away. You're left with C e to the 0, which is 1. Therefore, C is actually U0. Therefore, U is what you see there. This is working out pretty nice, but you should take the time to double check it. And therefore, if we write the solution of the du dt equation, or I'm thinking of the du dt equation being what you see there based on the matrix J, I'm using a psi instead of a phi because the variables boldface vector u instead of boldface vector y. Equals that, which I can write as a matrix times a vector. And this thing right there that you see there is the matrix exponential, and I'll check it in Mathematica at the end of the lecture. But wait a minute. How do we get back to y? We got to use the similarity transform again. P inverse AP equals J. P inverse AP equals J. Therefore, A must be PJ P inverse. But wait a minute. What's P? If we can find P, then we can do this. We can write the solution of the dy dt equation, where A is an arbitrary matrix, not necessarily upper triangular, that has lambda as a repeated eigenvalue. That's the point here. I know by the beautiful generalization that I've talked about, y would be e to the ta times y0. Then I can replace A with Pj P inverse, which, as I've shown before, is the same as P e to the Tj times P inverse. And this would be the answer if I can only figure out P. That would work, if I can only figure out P. But how do you figure out P if there's only one linearly independent eigenvector? Which is going to happen, actually, for the Jordan form. There's only one linearly independent eigenvector, and that's going to be the same thing as a matrix A with lambda as a double root, if it is similar to J. Alternatively, we can think in terms of Taylor series. This is worthwhile, so I'm going to rederive the same thing, but I'm going to use Taylor series. It's worthwhile to see that you get the same thing. It's also worthwhile for another reason, because it leads to the more general theory about Jordan canonical forms without getting into the more general theory. Note that T times J, which is the matrix I want to exponentiate, can be written this way. Why? Because the matrix J can be written as a sum of two matrices this matrix, which is lambda times the identity matrix, plus this matrix, 0, 1, 0, 0. And it turns out that that's actually a very good thing, because exponentiating that thing is easy. This is a 0 here. Exponentiating this thing, finding the matrix exponential of t times this in particular, is actually pretty easy too. We're about to see why. D and N, this is D, this is N. I am multiplying by N by T. Commute. And by the way, also notice that N squared equals the 0 matrix. Go ahead and square this matrix. This is the N. N squared is the 0 matrix. Check it out, it works. Interesting. You can square a non-zero matrix and get the 0 matrix. That doesn't happen with numbers, right? With ordinary real numbers or complex numbers. You can't square a real or complex number and get 0. A non-zero real or complex numbers in it. But it can happen with matrices. It's called nilpotent when that happens. D and N commute. D times N equals N times D. That's worth checking. Actually, I mean, D commutes with anything. It's the multiple of the identity matrix. Matrix multiplication in general is not commutative, is what I'm saying in the parentheses here. Because of this, because N and D commute under multiplication, it turns out you can write the following line. And the key step right there is because of the fact that they commute. E to the t times j, because j is d plus n, can be written this way. And I can multiply the t through like that, and I can also rearrange the order on top, which I did for a reason. I didn't have to do it, but. Then this is an exponential of a sum, and it should make some intuitive sense that it's the product of the corresponding exponentials. But that's actually not true if n and d don't commute. That's actually not true. You can try examples, maybe with technology. But if they do commute, it is true. This is one place where the exponentials are not obeying a property of real number exponentials or complex number exponentials. Oftentimes we've assumed that it carries over to generalized settings, but here it doesn't unless n and d commute. But e to the tn, in terms of a Taylor series, is this. We talked about that before. But remember, n squared is the 0 matrix. That term goes away. And if n squared is the 0 matrix, multiplied by n again, you're going to get the 0 matrix again. N cubed is also the 0 matrix. N to the 4th is, n to the 5th is, etc. I meant to put dot, dot, dots in there. This goes on forever, but I forgot to put the dot, dot, dots. But anyway, that's what happens in general. This series truncates. All the terms past the n to the first power go away. And it doesn't have to be written as an infinite series. It's I plus tn, which is this. So that's pretty simple. That goes there. And I know how to figure out that too. Therefore, e to the tj is the product of this matrix that I just found with e to the td. D is diagonal, lambda on the main diagonal in both spots. This is going to be e to the td. If you multiply these, you get this. And that is the same as the previous slide for the matrix exponential e to the tj. Do you believe me? Take a picture of it or write it down. Let's go back to the previous slide. Same thing as that, right there. E to the tj. I approached it with the method of undetermined coefficients here. On this slide, I'm approaching it with Taylor series. I get the same thing. Okay, very happy. Math is consistent. But what is the matrix P? We still haven't answered that yet. I still want to ultimately solve dy dt equals a times y. I will take a particular example of a here soon. What matrix P should I use? Its columns consist of a certain basis of R2. Oops, there's supposed to be an R in there. I have no idea why it went away. It was there before. I have no idea why it went away. That's supposed to be an R2. a certain basis of a plane of what are called generalized eigenvectors of A. A is not diagonalizable, so it does not have a basis of eigenvectors, regular eigenvectors. But it turns out it will have a basis of generalized eigenvectors. What's that? Here's a definition. In the general case, let A be an n by n matrix. Our example is going to be 2 by 2. Let lambda be an eigenvalue of A with multiplicity m that of necessity has to be less than or equal to n. A generalized eigenvector of A corresponding to the eigenvalue lambda is any non-zero solution of this equation for V. V has to be zero, non-zero, excuse me. Where K can be any number 1 through n. Remember, we talked about similar equations like this to solve for ordinary, regular eigenvectors for an eigenvalue lambda when K is 1. We had talked about that. Generalized allow K to be 2 or higher when lambda has a multiplicity of 2 or higher. Note, any eigenvector is also a generalized eigenvector. If K is 1, then you're talking about the regular, ordinary eigenvectors. So those will also be generalized eigenvectors. Here's our example, concrete example. Check that this matrix has a repeated eigenvalue of 2 with corresponding eigenvector negative 1, 1. You can take the time to check that. I'm not going to. Is there a generalized eigenvector that is not a regular eigenvector? That is not a non-zero multiple of this? Well, try K equals 2 and see what happens. Figure out, when lambda is 2, A minus 2i quantity squared, which is this matrix squared, that's the zero matrix too. That's also nilpotent. This matrix, negative 1, negative 1, 1, 1. Check it. It actually, when you square it, you get the zero matrix. Weird, but true. That's nilpotent too. And since that's the zero matrix, any vector that is not a scalar multiple of this, I should say any non-zero vector, I forgot the word non-zero, is a linearly independent generalized eigenvector. I mean, again, regular eigenvectors are generalized eigenvectors, but I'm after a second one that's linearly independent from this one. So pick any non-zero vector, forgot the word non-zero, that is not a scalar multiple of this, and you'll get a second linearly independent generalized eigenvector that we can then put in the matrix P to try to get A into Jordan canonical form. Still not the end of the story, though. Not just any old P will work. If we want Jordan canonical form with a 1 in the upper right entry, any such other vector will generate a matrix P that might give us something other than 1 in the upper right corner, but it won't be 0. To get to the Jordan canonical form in the present example, let P be of this form. So I've made the first column be the regular, ordinary eigenvector of P corresponding to the eigenvalue lambda equals 2. And I'm letting the second column be BD. That's going to be just some other vector that I got to figure out. Some other column vector that I got to figure out. That it better not be a multiple of the first column, because P does need to be invertible. Here's the formula for P inverse. 1 over the determinant of the matrix. The determinant of this is negative D minus B. Swap the numbers on the main diagonal. The D and the negative 1 get swapped. Negate the numbers on the off diagonal. Put negative signs in front of the B and the 1 to get negative B up here and negative 1 down there. But then I can multiply through by negative 1 to get a B plus D in the bottom there, and negate all these things to get a negative D, a B, a 1, and a 1. Remember, I don't want this column to be a multiple of this column. It won't be as long as B plus D is non-zero, and so I won't be dividing by 0. Yeah, if B plus D is non-zero, the second column of P is not a scalar multiple of the first, not a non-zero scalar multiple. So what's our goal now? Our goal is to see if we can figure out what B and D need to be so that when I convert A to the Jordan canonical form, I get a 1 in the upper right spot instead of some other non-zero number. So here, just calculate and see if you can figure it out. So there's P inverse AP, there's P inverse, there's A. It's our example. and there's P. Multiply these two, you get this. Multiply these two, you get this. Check it. Pause the video, check it. And that simplifies pretty nicely because you can cancel the B plus D's, and you get this. Remember the eigenvalues of our example, which is, again, this matrix right there. That's the A. Are both 2. 2 is a repeated eigenvalue, multiplicity 2. It's got to be on the main diagonal, no matter what B and D is. 0 down there is going to be upward triangular. So I evidently want to choose B plus D to make this 1 if I want it to be in Jordan canonical form. B plus D does not equal 0, because then I'd be dividing by 0. P would not be invertible. But I can make it equal to 1. We can choose B and D to be anything such that B plus D equals 1. We may as well take something simple like B equals 1 and D equals 0. And then P inverses that. I could also go to 0, 1. I could also go 17 there and 16 there, or excuse me, 17 there and negative 16 there. But you might as well keep it simple. So what this means is we now can find, for our particular A, which again is this matrix right here, we can find the matrix exponential times y0. There is P times e to the tj times P inverse. You can double check it equals this. I double checked it. That is going to be our unique solution of this generic initial value problem. Okay? It works and is not too bad for an example in the 2x2 case. Let's end with looking at Mathematica, just to confirm these calculations. If you try to find the eigensystem of this matrix, you get the repeated eigenvalue, and you get the single non-zero eigenvector. That is not an eigenvector. When you have a degenerate case like this, where the multiplicity of the eigenvalue is 2, and you've got just a single linearly independent eigenvector, Mathematica does make the other thing 0 to kind of alert you to it, but don't think that this is an eigenvector. It's not. It's in the eigenspace, but it's not an eigenvector. What is the matrix exponential of e to the tj? It is this one that we did show on a couple slides. This is just confirming that this matrix is nilpotent. Here's our P matrix. I think that was the one we used. Yeah, that was the one we used. The inverse of P, P inverse times A times P, does give you the J matrix. If I use this matrix, I actually do not get the J matrix. Oh, excuse me, I do. Again, because B plus D is 1, sorry. That gives me the J matrix as well. If I do something other than the case where B plus D is 1, like if I put a 3 there or something, then B plus D is not 1, it's still upper triangular, but it's not in Jordan canonical form. It's something other than 1 up here. But you'll never get a 0. I'll get rid of that now. Yeah, there's our derivation of P inverse times A times P that I'd like B plus D to equal 1 with. There's confirming I could use 17 and negative 16, etc. I can enter J, I can find the matrix exponentials. These are the same. That's e to the ta right there, and that's P times e to the tj times P inverse. They're the same thing. And I can multiply them times the initial condition as well. Okay? So it can be done. And again, the theory is not too bad in this 2x2 case with an example. Again, my students, you should study the repeated eigenvalue case in section 3.5 and compare. You get the same answer either way. Nice little introduction to an advanced topic. We may mention it again, but we're not going to really focus on it from now on. Thanks for watching.